As you can see in this video, we are going to be looking at the objective is that students will be able to identify and apply L'Hopital's rule to evaluate a limit. So let's refresh our memory on what a limit is. So if you go back to the beginning of the course, you will recall that a limit is a y value that is found on a function. You are approaching that y value as you approach a given x value. So that's from the beginning of the year. Finding a limit is basically finding a y value. And by the way, you will probably need to pause the video as you're going to take the notes, particularly students who are in my class. You're going to want to take the notes in your packet, so you may have to stop the video to be able to catch up and write down what's going on. So we're focusing on limits, and a limit is a y value. And as I said, L'Hopital is going to give us another strategy to find a limit under certain situations. So when we started finding limits at the beginning of the year, we started by finding limits graphically. And remember, when we find limits graphically, we want to ensure that the left and right limits agree. Left and right limits agree. So we would look at the graph coming from both sides to see if the graph coming from both sides of the given x value was approaching the same y value. Then we examine a little bit finding limits numerically, and numerically simply means we're using a table of values to see what y value is being approached. So it's really the same thing. It's just another strategy of finding a limit. And the third strategy that we used for finding limits was analytically. So if I give you a function, how do you find that limit? And some of the strategies that we talked about when we were finding limits analytically is we would do things like direct substitution. That's the first thing that we always try. And we really hope that we're not approaching a discontinuity, because direct substitution is nice and easy to find the limit. But if direct substitution didn't work, we did things like factor, reduce, and then substitute, because in that case we were probably approaching a discontinuity, so we had to remove the discontinuity in order to do the direct substitution. We did things like algebraic and trig manipulation, where we would rewrite the expression. And again, in most of these cases, we were trying to remove a discontinuity so that we could actually use direct substitution. Again, things we did early in the beginning of the year. So let's look at an example that we actually dealt with way back in the fall. Consider the given function. So notice that we're finding the limit. Let me get my pen here. We're finding the limit as x approaches 3. That's the x value that we're moving towards. And we are on this rational function right here, variable in the numerator and variable in the denominator. So the first question that we want to consider, is this given function continuous at x equal to 3? Well, we know this function is not continuous at x equal to 3, because if we substitute 3 in place of x, we have a 0 in the denominator, and division by 0 is undefined. So that answers question B. What happens if we try to use direct substitution? There's a 0 in the denominator, and we know that division by 0 is undefined. So we know that there is a discontinuity at x equal to 3. We already know that. What kind of discontinuity would this be? Well, the kinds of discontinuities that we could encounter are an infinite discontinuity, which graphically manifests itself as a vertical asymptote. We could have a jump discontinuity, which manifests itself as a jump. And we can have a point discontinuity, which manifests itself as a hole in the graph. So the fact that I have, if I substitute 3 into my denominator, that I get 0, my first suspicion would be that we might have a vertical asymptote here, but I'm not 100% sure, because I can algebraically manipulate this expression to possibly remove the discontinuity. Now, hopefully you're noticing that square root in the numerator, and when we were finding limits way back in the day, hopefully you will remember that one of the strategies that we would use in a case like this would be trying to rationalize the numerator, which basically means try to get the radical out of the numerator and into the denominator with the goal of removing the discontinuity. And the way that we did that is we would multiply both the numerator and the denominator by the conjugate. The conjugate is, so I have the square root of x plus 1 minus 2. The conjugate would be the square root of x plus 1 plus 2. So that would be our strategy. So let's go ahead and uncover here. Is the function continuous at x equal to 3? No, it's not. If not, what kind of discontinuity occurs? So in this case, f of x is not continuous at x equal to 3 because f of 3 is not defined. And whether you know it or not, there is a removable discontinuity, a point discontinuity. There would be a hole in the graph. And we're not going to show that algebraically, but the way that we would show it algebraically would be following this process of rationalizing the numerator by multiplying numerator and denominator by the conjugate. And if we did, we would remove the discontinuity to see that there's going to be a hole in the graph. Now, below in part C, I have provided you with a table of values that are directly from this function. And remember that we are finding the limit as x approaches 3. So look at these x values right here, 2.9, 2.99, 2.999, and 3 is right here in between 3.001, 3.01. So when we come from the right side, and this would be coming from the right side, as we travel towards the x, sorry, I literally wrote from the right side. Whoa. This is the left side. This is the right side. So as we come towards the x value of 3 from the left and the x value of 3 from the right, what's happening with the y values? So let me uncover this little box, and you will notice that in terms of y values, when we come from the left side, we have 2.5158, 0.25016, 0.25002, and then coming from the right-hand side, you can see these decimal values, and on both sides, we are approaching a y value of 0.25, or 1/4. It could be written either way. So the limit as x goes to 3, and again, we haven't done this algebraically, and we're not going to because I'm going to show you a new strategy for that. But the limit as x approaches 3, the y value that we're approaching on this graph, which I have provided over here on the right-hand side of this function, is a y value of 0.25. Remember, a limit is the y value that we approach, but we don't have to reach it. You can see from this portion of the graph that I have provided for you, here's the scale is 1, and as I travel towards the x value of 3, that y value is 0.25 on the left side, and that y value is 0.25 on the right side, verifying that, yep, the limit as x goes to 3 of this function is 0.25. And you can see graphically there is a point discontinuity. Now, would you provide those table values without a calculator? No. Would you sketch this graph without a calculator? Not likely. So what would be your strategy? Well, back in the day, as we have said over and over and over again, we would rationalize the numerator in order to remove the discontinuity and analytically find the limit. However, I'm going to introduce you to a friend, and his last name is L'Hopital. It's not hospital. It's not hospital's rule. It's not low hospital. It's L'Hopital's rule. And L'Hopital was French, and he was a French mathematician, and this was just one of his contributions to mathematics. So letters F through H are going to walk you through L'Hopital, and then we're going to formalize L'Hopital's rule. First, I want to bring your attention right down here to, what letter is this? I guess it's letter G. Notice that on your paper, if you have the notes from my class, Please fix this. It says the limit as x approaches 3. No, actually, I don't want a 3 there. I had it right the first time. So ignore that, delete, and ignore that, delete. So I had exactly what I wanted. So we're all good. So notice what I've done here is in L'Hopital's rule, we're going to examine the numerator independently. So I basically have taken the numerator off of the function and I've taken the denominator off the function, and you'll see that we're going to examine each of those independently right here of each other. So I'm naming the numerator f of x, and I'm calling the denominator g of x. When I find the limit as x approaches 3 in the numerator alone, I get a y value of 0. And having a y value of 0 in the numerator is never a problem. When I find the limit as x approaches 3 of x minus 3, that would give me 3 minus 3, which is also 0. And having a 0 in the denominator is a problem because we know that division by 0 is undefined. So again, the fact that the numerator limit is 0 is not a problem. So that's okay all by itself. But having a 0 in the denominator is a problem because division by 0 is undefined. So we're going to have to remedy that. And again, we're examining the numerator and denominator independently of each other. So according to L'Hopital, once we get into this situation, and I'm going to explain more about what has to happen before you can use L'Hopital. One case of L'Hopital, because he applies to more than one case, is when I have a 0 in the numerator and a 0 in the denominator. So what we're going to do is we're going to find, as you can see right here, find the derivative of the numerator independently, find the derivative of the denominator independently. So stop the video, find the derivative, and then see if you get the same thing that I got. So for the derivative of the numerator, I'm going to have 1/2 x plus 1 to the negative 1/2 power. Because the variable on the inside is x, by the chain rule, I don't need to worry about the derivative of x, which is 1. So that's the derivative of the numerator. The derivative of x minus 3, the denominator, is just 1. So that's easy. Okay, after we find the derivative of the numerator independently and find the derivative of the denominator independently, now we're going to substitute 3, which is the x value that we are approaching. I'm going to substitute 3 into f prime. I'm going to substitute 3 into g prime. And then I'm going to find the limit as x goes to 3 of f prime of x over g prime of x. So stop the video, find the derivative of f at 3, the derivative of g at 3, and see if we agree. When I find the derivative of f at 3, notice that I'm going to move the negative 1/2 power right here. I'm going to move that to the denominator. I'm going to substitute the 3. 3 plus 1 is 4. The square root of 4 is 2. And 2 times 2 is 4. So when I substitute 3 into the derivative of the numerator, I get 1/4. When I substitute 3 into the derivative of the denominator, which is always 1, oops, let me uncover that, 1/4 or 0.25 for that. Substituting the 3 into the derivative of g gives me 1. Now the last thing that I'm going to do, notice I'm finding the limit as x approaches 3 of the derivative of the numerator over the derivative of the denominator. And I want to emphasize very strongly, can't emphasize strongly enough, this is not the quotient rule. In no way am I connecting this or trying to tell you that we have performed the quotient rule. We absolutely have not. It's the derivative of the numerator independently over the derivative of the denominator independently, and we're finding the limit as x goes to 3 of that. So we already knew that the derivative of the numerator at 3 is 0.25. The derivative of the denominator is 1, so I end up with 0.25 over 1, which is 0.25. Now think about it. What do you notice about the quotient of the derivatives, or the limit of the quotient of the derivative as x equals to 3 versus the overall limit that we found on the first page by table and by graph. Hopefully you're noticing, aha, it's the same thing. So L'Hopital can help us to avoid doing that rationalizing the denominator and going through all of that algebraic, quote, mess. So this is an example. That was a real slow walkthrough of L'Hopital's rule. So let's see what L'Hopital's rule says. Conditions of L'Hopital's rule are f and g are differentiable, have a derivative, and if f and g are differentiable, we know that differentiability implies continuity. And f and g must be differentiable on an open interval that contains the value of x that we are going to approach. So in this case, x is approaching a. I have a quotient. F is differentiable. G is differentiable. Now, L'Hopital says I can only help you under very, very specific conditions. If you substitute a into the numerator and denominator and you get either 0 over 0 or any combination, listen to that again, any combination of infinities, meaning positive infinity over positive infinity, negative infinity over negative infinity, positive infinity over negative infinity, negative infinity over positive infinity. Only on those conditions, L'Hopital says, if that happens when you find the limit as x approaches a of your original function, f over g, then what you can do is you can find the limit as x approaches a of the derivative of the numerator independently divided by the derivative of the denominator independently. And when you substitute a into that, it will give you the limit of the original function. All right, these forms right here are called indeterminate forms. And there are other as you can see right here, this rule works on other indeterminate forms as well, but these are the only indeterminate forms that we will study in AB calculus. All right, so let's see how L'Hopital's rule works in a situation. Now, as I do these examples, pay very, very, very close attention, because when you do your work, it must be done exactly verbatim as I show you. So here we go. If I were doing this problem on an AP test and it said find the limit as x goes to 0, then what I would do is I would substitute 0 in. I would try direct substitution and hope things are going to go well. So if I substitute 0 in place of x, e to the 0 is 1, and 1 minus 1 is 0. When I substitute 0 into x in the denominator, I get 0, and so I have one of the indeterminate forms that L'Hopital can help me with, 0 over 0. But I may not write 0 over 0. What I do in my work and what I expect you to do in your homework is to show the following steps. Step number 1, find the limit as x goes to 0 of the numerator. So limit as x goes to 0 of e to the 3x minus 1. We said when we substitute 0 in place of x, we get e to the 0, which is 1, and 1 minus 1 is 0. Numerator. Same thing in the denominator. We're doing these independently of each other. The limit as x goes to 0 of x is clearly 0. Do not write 0 over 0, or you will be knocked out of the possibility of getting L'Hopital credit. So what happens now is that this says, now you may call L'Hopital because it's one of the indeterminate forms that L'Hopital can help. So I'm going to write by L'Hopital. Now remember what L'Hopital says. he says you're going to do the same thing. You're still going to find the limit as x goes to 0, but you're going to take the derivative of the numerator. So the derivative of e to a power is e to the power times the derivative of the power. The derivative of 1 is 0. The derivative of x is 1. Okay, so I've taken the derivative of the numerator, derivative of the denominator, and now I'm going to substitute 0 again. So e to the 0 is 1. 1 times 3 is 3, so I have 3 over 1. So now I know the limit. Without doing any sort of algebraic manipulation, I used L'Hopital's rule. So actually the by L'Hopital applies to that piece right there. That is exactly how you have to show your work for every single problem. All right, I'm going to skip letter B, and I'm going to go to letter C. So, limit problem, I'm going to try direct substitution. So I'm going to find the limit as x goes to pi over 2 of secant pi over 2, which is the same thing as limit as x approaches pi over 2 of 1 over cosine pi over 2, and cosine of pi over 2, the x value of pi over 2 is 0. All right, I'm going to do the same thing with the, remember it's independent, so now I'm going to do the limit as x approaches pi over 2 of 1 plus tangent x. So that is going to be 1 plus tangent of 0. The tangent of, oh, I'm sorry, it's pi over 2. Whoa, let's back that up a little bit. I was going to say, something's not working out right here. 1 plus tangent pi over 2. The tangent of pi over 2, remember tangent is sine over cosine. The y value at pi over 2 is 0. So this is going to be 1 plus 0 over 1. The cosine of pi over 2, I think I said that backwards. The sine is 1 over 0. So notice that I have a 0 in the numerator, which is for L'Hopital, that's a good thing. And here I have 1 plus 1 over 0. This is not equal to, so this expression is not equal to 0. All right, so L'Hopital can't really help me out here, but because I see now that I'm going to have that 0 in the denominator of tangent, you may or may not realize that that really tells me that I'm going to have a vertical asymptote in this function, and therefore the limit does not exist because of unbounded behavior. So this is a situation to say, don't assume that everything is going to turn into L'Hopital, because this doesn't give me a situation that I can use L'Hopital for. So that's kind of the moral of the story behind letter C. All right, let's go on to letter D, which is going to take us back to L'Hopital. So notice now I'm approaching infinity. So I'm going to find the limit as x goes to infinity of Ln of x. Now for this one, you sort of have to know what the graph of the the graph of Ln looks like. Remember, it goes through the point 1, 0, and it grows slowly, but it grows slowly over time and travels towards infinity. So we are approaching infinity as we go toward, as x goes to infinity, the y goes towards infinity. And then when I find the limit as x goes towards infinity of 2 square root x, even though we're substituting, in air quotes, substituting infinity in place of x, 2 times the square root of infinity is approaching infinity. So I have the situation of infinity over infinity. So L'Hopital says I can help you with this because this is one of the indeterminate forms that I will deal with. All right, so now that we know that we can invoke L'Hopital, we're still going to find limit, but we're going to find the limit. Remember, you take the derivative of the numerator. Limit as x goes to infinity. Feel free to stop, try this on your own, and resume. The derivative of the ln of x is 1 over x, and the derivative of 2 square root x is, remember, this is 2x to the 1/2 power, so half of 2 is 1, x to the negative 1/2. Okay? So when we, let's see, how do we want to clean this up? This is the same thing as limit as x goes to infinity of, we'll write it like this, 1 over x over 1 over x to the 1/2 power. I have a negative power right here, so I can move that to its own denominator. This is my big fraction bar right here. All right, so I can multiply by the reciprocal, so that becomes x to the 1/2 over 1. So I can get rid of that, just multiplying by the reciprocal to clean the fraction up. I can rewrite that to be limit as x goes to infinity. So I have x to the 1/2 power in the numerator and x to the first power in the denominator, which becomes 1 over x to the 1/2 power. And remember, when we have one piece of bubble gum, if I substitute infinity, air quote substitute infinity in place of x, one piece of bubble gum in the numerator divided into infinite parts means that everyone's getting virtually no bubble gum. The fraction as x goes to infinity approaches 0 by L'Hopital. And I don't think I wrote that in, but right here is where we're doing by L'Hopital. All right, let's do one more of these, and then I'm going to, where you're in my class, you'll have an assignment, and you should do your assignment exactly the way that I'm doing these problems. So notice this is an intentional statement. Sometimes we need to repeat ourselves. Sometimes we need to repeat ourselves. What does that mean? Well, let's play the game again. I'm trying to find the limit as x goes to negative infinity. So if I air quote substitute negative infinity and square it, the limit as x goes towards negative infinity of x squared approaches positive infinity. And the limit as x goes to negative infinity of e to the negative x, so I have negative infinity, negative x, that would be e to the positive infinity, which is going to infinity, so I have infinity over infinity, so I can apply L'Hopital. So L'Hopital says, all right, we're going to find the limit as x goes to negative infinity, derivative of the numerator, 2x, over derivative of denominator, e to the power, times the derivative of the power. And now I'm going to, quote, substitute negative infinity again. So the limit as x goes to negative infinity of 2x, so 2 times negative infinity goes to negative infinity. The limit as x goes to negative infinity of negative e to the negative x. So if I substitute negative infinity times a negative makes positive infinity, which is going to positive infinity times a negative makes negative infinity. Huh. So I get another situation that says L'Hopital works again because I got another negative infinity over negative infinity. Look right here. Sometimes we need to do it again. So L'Hopital says, well, if you didn't get an answer the first time, try it again. Step 3, phase 3, limit as x goes to negative infinity, take the derivative again. 2, take the derivative again, e to the power times the derivative of the power. All right, now the numerator has no variable in it, so basically I'm taking 2 pieces of bubble gum, and when I substitute e to the negative, oh, that's a negative x. I almost messed that up. Let's fix that. For those of you who already caught that and said, uh-oh, you forgot a negative, good for you. Good for me that I caught it. Okay, so when I substitute negative infinity times a negative, I get e to the positive infinity. So in the denominator, I get positive infinity. 2 pieces of bubble gum shared with infinite people means that everybody virtually gets nothing, gets 0. So the y value being approached on the original function is a y value of 0. So in summary, L'Hopital's rule. What is it used for? And you can stop the video as needed to copy this down. L'Hopital's rule is used to determine the limit of a quotient for the indeterminate forms of 0 over 0 or any combination of infinity over infinity. What conditions have to be in place? The numerator and the denominator must both be differentiable and continuous on the interval that contains the value of x being approached. What do you have to show? You have to show the limit of the numerator and the limit of the denominator independently. Do not write 0 over 0 or the infinity over infinity. Show those limits independently. And then what do you do once you have met all these criteria? Take the derivative of the numerator, take the derivative of the denominator, find the limit of the quotient of the derivatives, and repeat as often as necessary. So this is the lesson on L'Hopital's rule. If you are in my class, you will go to your assignment sheet, complete the assignment, make sure that you read the directions very carefully. You're doing the work on separate paper, and you're circling the answer in your packet.